Now it's time to do some NLP, natural language processing, and we will start with the famous word-to-vec example. So word-to-vec is a way to compress your multidimensional text data into smaller sized vectors, and with those vectors you can actually do calculations or further attach downstream neural network layers, for example for classification. And in this case we will just do both. So we will start with some imports, and we put here a seed that the examples are replicatable. So let's start with some sentences. So this is a document which has 5 sentences, and 4 are related to queens and kings and so on, and men and women, and 1 is unrelated. We define vocabulary size 50. That means this system here as it is will support 50 different words. In a real life scenario, of course, you have millions of words. Later we do some calculations with the words, therefore we already now get the representation of these words, and I will show you what I mean by that. So each word is just a sequence of characters, and obviously we cannot work with a sequence of characters. Therefore we will convert each word into an integer number, and this integer number is unique as long as we don't exceed the vocabulary size. Note that the function is called one-hot, but in my opinion that's not correct. It's not the one-hot encoding, it's basically just a transformation from a list of words into a list of integer values. As you can see here, I'm correct. So for example, king is number 23, and queen is number 26, or man is number 22, and so on. So now we are actually one-hot encoding this stuff. So this is now a single dimension with multiple values, and one-hot encoding returns multiple dimensions, and only one of those dimensions has a 1, the rest is 0. That means we are getting sparse vector representations. So that's actually what I'm talking about. So you see here for each word we get a sparse vector, and if the particular word is present at that position we have a 1, otherwise we have a 0. So now we have done this for our example words, but now let's do it for the complete document. So as you can see here, we have some words again. So those are the sentences. So each element in this multidimensional array is a sentence, and each integer is representing a word. It's just an index which tells us at what position we should insert a particular word. So 23, 42 and 22 are actually king is man. So king is 23. So we see here again king as second word in the second sentence. So here we are actually padding. That means if the sentence is not long enough, we are just filling it with zeros. And now this function is very important and maybe a bit complicated to understand, but what we are doing is we are now creating tuples, and we are creating tuples of a word and the related words. So in a sentence, for example, king is man, if you look at the word king, then we are creating tuples where king is the key and is the value, and king is the key and man is the value. So that means that's the embedding. That means the neighbors of the word. So we are creating a list of tuples where for each word we also are assigning the neighbors of the word. And we are doing this in this case for 2 neighbors, for 2 preceding neighbors and 2 succeeding neighbors. Don't lose too much time with that nested for loop here, just look at the result. So the result has a dimension 38 by 2, that means we have 38 word pairs, and the pairs, as the name implies, have dimension 2. So again we have now 2 dimensions with integer keys, and in order to make a neural network perform, we again have to encode it as one-hot encoded vectors. So we first do it for the first dimension, which basically resembles in the input x to the neural network, and then we do it for the second dimension, which is our target. So that's what we want to predict, and that's the y, or the output of the neural network. So here you see that again we have 38 dimensions, because in the previous example we had 38 pairs, but now we have 50 dimensions, because now the one-hot encoded vector representation is a sparse vector of size 50, and remember only one of those elements is 1, and that's the position which actually reflects the word. So we start with a dense input layer which has 50 internal neurons and also expects dimensionality of 50. So actually that perfectly matches our one-hot encoded vectors of size 50. And we use ReLU as activation. So now it gets interesting. Now we are introducing the bottleneck. Remember, bottlenecks we have in autoencoders. So this is an autoencoder what we are building. And the bottleneck has only 2 dimensions. And again, activation function is ReLU. And in an autoencoder, of course, we have to map again to the same dimensionality. So because input was of dimension 50, also the output has to be of dimension 50. So we are mapping sparse vectors to sparse vectors. That means we are mapping words, for example a word in the center, to words in the neighborhood. And while we are doing this, we are training the bottleneck layer, and that's our low dimensional representation. And that's actually what word2vec does. It creates a low dimensional representation of our high dimensional word embedding, which then basically is a low dimensional word embedding. We compile, set optimizer and loss function, and then we call fit. So that starts training on the one-hot encoded labels X and the one-hot encoded target Y. So for this Mickey Mouse dataset, this goes really fast, and we are quite happy with our loss and accuracy. So now it gets even more interesting. Now we build a new neural network, but we are reusing 2 of the 3 already trained layers of the previous neural network. So we start with a sequential model again, and we add the already trained input layer, and we add the already trained bottleneck layer. So if we now compile this neural network, the input still is 50 dimensional, but the output now is only 2 dimensional. So we take our 5 words of the beginning, and let's see what the 2-dimensional representations of those words are looking like. So we see this is an array of 2-dimensional vectors, and we in theory can now plot those words into 2D space. But we can also calculate with those vectors. So we now take the word king, we subtract man, we add woman, and this should resemble in nearly the same vector as the word queen. So that means if we now subtract queen from it, we should get a relatively low value. Since this is only a toy example with very little data and training takes a lot of time, I'm using some online demo of this system. So here we actually take woman, and here we say king minus man. So we get somehow the meaning of king without a gender. And if we add this meaning without a gender to a woman, we should get queen. Let's see what happens. Yeah, see, we are pretty close. So that's actually really cool. We can now calculate with words in a low dimensional vector space.